So, I'm going to talk about terminal velocity. Put simply, the scenario we're nearly always talking about, it can be about a car reaching a top speed, but we normally talk about it as if a falling object on Earth, usually a parachute. So I'm just going to begin by considering what happens on the moon. So, objects on the moon fall at a constant acceleration. They do this because there is no atmosphere and hence no air resistance. So if you consider the scenario we're seeing here, what this is it's a I believe this is in Russia. It's a chamber somewhere where all the air could be sort of pumped out of this area, and on the top left, you're seeing what happens with the hammer and the feather, as the famous experiment on the moon. When all the air is pumped out, you can see they fall at 9.8 meters per second squared, or they accelerate at that rate, and they basically hit the ground at the same time. Whereas in the top right there, you can see what would happen when there's air, and as we would expect, the cannonball or the bowling ball falls a lot faster than the feathers. Okay, so this is the scenario that's happening here. So you need to describe this in terms of forces and in terms of acceleration. Okay, so you can see when the ball is just dropped, we're ignoring horizontal forces when we're talking in this scenario, and we can see there when the ball is just dropped, really the only force acting is the weight, and that accelerates the ball at 9.8 meters per second. Is at this point it has not really any velocity. Okay, and then after some speed is built up, the air resistance, the drag force, the air resistance increases, and this reduces the resultant force acting on the object, which is obviously the sum of the two forces. So it might be sort of about this big if I were to draw it. Okay, and then finally, in the final picture, we can see terminal velocity. The air resistance is is equal and opposite the force of weight. So the forces are in equilibrium. The resultant force acting on the object is zero, and the object has reached terminal velocity. Okay, so it's now falling at constant speed. The acceleration is zero. Okay, I'm just going to show you that quickly in terms of so we've got a velocity time graph here, where the acceleration is represented by the graph. So at the beginning, the gradient is 9.8, and the object quickly gains speed. The object continues to gain speed even as the air resistance increases. So never say that it's decelerating at this point. It's not decelerating, it's still accelerating, it's just not accelerating strongly, and the resultant force is less than it was previously. Finally, we reach terminal velocity. We say the resultant force is zero, the forces are in equilibrium. Okay, and then quite often you might need to talk about the scenario when the parachute's opened, where we say at a given speed, the air resistance is much greater because the parachute shows a much greater surface area. And so what happens here is for a period of time, the resistive forces are much greater than the force of weight driving the downward movement, and the object, the resultant force is acting opposite the direction of movement, and the object is decelerating. Now, it's not going up, that's a misconception that's sometimes brought up, but it is basically going to slow down at this point, and as it slows down, that is going to cause the air resistance to decrease until we reach a new terminal velocity at a slower speed, one where we have a different object, a bit like the cannonball and the feather. We now have more closer to the feather scenario, where the object is falling at constant speed, but as it has a different shape, the speed is a different terminal velocity, where the upward force is provided by the contact force with the ground.